Okay, folks, here we go. Antiderivatives, also known as integrals. That's just another name for an antiderivative. Here's all you're doing. If you've got a function, let's start with x to the fifth power. I want to remind you, today most of what we're going to be doing is just your power rule. In order to find the derivative, which is what we spent the last 4 or 5 chapters on, in order to find a derivative, we're moving a power down front and taking one away from the power. Again, that's called a derivative. What we're doing today are antiderivatives or integrals. We're starting with the derivative form and we're trying to go backwards. So let's try to develop a rule that we can use to find an antiderivative. So here we go. From x to the fifth to 5x to the fourth, again, we took one away from the power. So the most obvious thing that we're going to have to do is to go backwards. We're going to have to add one back to the power. Something else we did with this power was we multiplied it down front. Okay, the old power, the 5. So we're going to add one back to it. In order to get from point A to point B, again, we multiplied out front. So to go backwards, we're going to divide. So again, we multiplied and took one away. So it's kind of like inverse functions that we did back in pre-calculus. If we multiply, took one away, then to go backwards, we're going to add one and divide. That's simple backwards antiderivatives, backward derivatives. And that's what we're going to be starting with today. Is we're going to be given some general, and like I said, most of them are going to be power rules. And this is going to be our rule for our power rules. Add one and divide by the new power. The function is 6x to the fifth power. Again, it's going to say find the antiderivative of that. Add one to the power, divide by the new power. So add one to the power, you're going to get x to the sixth. Divide by the new power, which is 6. 6 divided by 6 cancels. And I highly suggest is on these, check it by doing this. Find the derivative of your answer. Bring it down, take one away, you do get 6x to the fifth. But I want to introduce a problem to you. We're saying the antiderivative of the 6x to the fifth is x to the sixth. Let's check it by finding the derivative of x to the sixth. We do get that, but what about this problem? What if you got x to the sixth plus 7 and I ask you to find the derivative of that? Is it 6x to the fifth? Yes, because the constant derivative is always 0. What about x to the sixth plus 8 or x to the sixth plus 9? If you find the derivatives of any of these, you get 6x to the fifth power. So, really, truly, in order to find the antiderivative of 6x to the fifth, it could be x to the sixth plus any constant. Here's how we fix that. When I ask you to find an antiderivative, we're going to, again, add one to the power, divide by the new power, we get x to the sixth, tack on a plus c. Because what that is, that could say your answer is x to the sixth plus any number. Because if you were to find the derivative of this now, this part does go to 6x to the fifth like we want. This part would always go to 0. So it's x to the sixth plus any constant would have a derivative of 6x to the fifth power. Okay, next one. Let's find the antiderivative of x to the eighth power. Now we're getting a little bit more difficult. The antiderivative of x to the eighth, we're going to add one to the power, divide by the new power. Okay, before we had stuff that cancels, here it doesn't. So we're going to divide by 9, and you can write that as division by 9. I would like for you to get into a habit of putting 1/9 instead of dividing by 9. Plus the constant. Again, let's check it. To find the derivative of 1/9 x to the 9th, bring it down. 9 times 1/9 would cancel each other out. Take one away, and you do get x to 8. And then plus the constant, the derivative of that would be 0. Okay, the next one. The antiderivative, and I'm going to start saying integral. The integral of x squared plus 11x plus 28. Integral is the technical term for an antiderivative. It sounds better. But they are the exact same thing. We say antiderivative because it's just a backwards derivative. So, and we'll start on notation on the next one. The antiderivative or integral of x squared plus 11x plus 28. It looks a little bit harder, but it's not. All you're doing is you're splitting this three ways. This is three separate problems. Find the integral here, the integral here, the integral here, and you're finished. The integral of x squared, you're going to add 1 to the power and divide by the new power. It's 1/3 x to the third. Plus, the integral of 11x, we're going to add 1 to the power and divide the 11 by the new power. So you have 11/2 x squared plus 21x to the 0. There's no x's there. So 28, I think I said 21, 28. Add 1 to the power, x to the 0 turns into x to the first. You don't really have to put that 1 there. Divide by the new power, which would be 28 divided by 1 is 28. That should make sense because if you find the derivative of 28x, that x goes away. Bring the 1 down, take 1 away, you have just plain 28 then, plus a constant. There's the antiderivative. Okay, next one, the integral of negative 4x to negative 5. Okay, now let's talk notation. We know that derivatives look like this. We've found the derivative with respect to x, or sometimes we call it y prime. Sometimes we call it f prime of x. Those were all notations for derivatives, or dy dx. Okay, any of those were notations for derivatives. If I'm talking antiderivatives or integrals, it's this funny looking S thing. Is the notation for integrals. So what we're going to integrate here, we're going to find the integral of negative 4x to negative 5, and they'll tack on at the end a dx. Let me explain what that means. You're going to integrate this with respect to x. X is your variable. You're going to treat x like a variable. It's just like this. dy, the derivative of y, with respect to x. Okay, this dx that we're tracking on the end simply is telling you what you're integrating with respect to. What is my independent variable? So if you see the integral sign, that's all it means. The integral with respect to x, you're doing the same stuff to this right here. The integral with respect to x is equal to. We add 1 to the power. Negative 5 plus 1 is negative 4. And we're going to divide by the new power. Negative 4 divided by negative 4 is simply 1. Plus c. You can check that, move the negative 4 down front, looks just like that. Take 1 away from the power, looks just like that. We're done. Don't forget to tack on your plus c. Next one, the integral of 7 over x squared with respect to x. On these, they look a little bit harder because the x squared is on the bottom, so put the x squared on top. If it doesn't look like a problem that we've worked thus far, make it look like that. X squared, when moved to the top, becomes x to the negative 2. Now it's the same thing. Add 1 to the power, you get x to the negative 1. Divide by that new power, negative 7 divided by negative 1, or excuse me, 7 divided by negative 1 is negative 7, plus c. And if you want to write it back like it started with a positive exponent, you can bring that x to the negative 1 back to the bottom. That would be negative 7 over x plus c, which looks a little bit better because now you have positive exponents. Next problem, the integral or antiderivative of negative 7 cosecant x cotangent of x. Let me show you a trick here. Let's go back and talk derivatives for just a second. If I ask you to find the derivative of a function was 2x to the 5th. I told you that anytime you're finding a derivative of a function, if you've got a coefficient out front, that you can go ahead and bring that coefficient down. Kind of what you're doing is moving that coefficient out front and then find the derivative of the x stuff. You can do the same thing here. And please do that. If you're ever integrating something with a coefficient in front of it, move the coefficient out front and just integrate the other stuff. Coefficients can be transferred through that integral sign and you don't have to worry about them anymore. Then you just bring them down. And the integral of cosecant cotangent, let's see if I've got my formula sheet here. This is the formula sheet I believe I gave you. And let me find it here. Cosecant cotangent is here. The derivative of cosecant is negative cosecant cotangent. So therefore, the integral of negative cosecant cotangent is cosecant. It works again backwards and forwards. So what I should have actually done, go back to my screen, what I should have actually done was leave that negative inside with it. Let's do that. The negative's back inside, and I should have just brought down a 7. Because now the integral of negative cosecant cotangent is just cosecant. Tack on the plus c. So 7 cosecant, and you can check that. That means, slide that down a little bit. You can check that. Again, leave the 7 out front. The derivative of cosecant would be negative cosecant cotangent. That's where that negative comes from. So you do get back where you started. And then the derivative of c, of course, would be 0. Okay? The integral of e to the 8x dx. You've got to be careful with these because we're not going to do a lot of chain rule stuff today. This one is, though. So you've got to be cautious with how you do this because we've got to find out, again, think about what an antiderivative is. We're looking for the derivative of what is equal to e to the 8x. And a quick reminder, the derivative of e to the x was e to the x. So you would think, well, the derivative of e to the 8x is e to the 8x, but you've got to be a little bit careful with that. Because, again, we're looking for the derivative of what is equal to this. If I were to differentiate this, I would get e to the 8x, but then you have to go inside and you have to differentiate this as well, right? It's chain rule. The derivative of this is 8e to the 8x, not e to the 8x. So how do we fix that? We put something out front that will cancel that 8. Now try to differentiate this. The 1a is a coefficient, it stays put. The derivative of e to the 8x, again, is e to the 8x, but by the chain rule, you have to go inside and find the derivative of that 8x as well, which would be 8. Put something out front that will cancel with that if there's nothing there. So now the derivative of 1/8 e to the 8x would give you that e to the 8x. Because you're able to cancel out, you're kind of like canceling out that chain rule. Okay, next one's to integrate radicals. I just want to remind you that, and this, you think back and you wonder why we talk so much in pre-calculus about how to change from radical form to exponential form and back and forth. This is why. Because hopefully you know and you've seen it enough, anytime you see a radical, it is simply an exponent. And that's what you're going to do. Anytime you're integrating a radical, change it into the other form. Change it into exponential form. The 14th root of x would be x to the 1/14th power. The 15th root of x would be x to the 1/15th power. And again, an integral of two things being added is simply two separate problems. And if you even wanted to split it up, some books will make you do this. They'll make you split it into the integral of x to the 1/14th dx plus the integral of x to the 1/15th dx. And it's simply two different problems is all you're doing. This that I'm about to show you is something you're going to get really good at. Okay? Add 1 to the power. 1 whole is 14 out of 14. When you add 14 out of 14 to 1 out of 14, you get 15 out of 14. That's one thing. That's going to make you a little bit better with your fractions. Again, what I did was added a whole. I added 14 out of 14. I now have 15 out of 14. Now this is the part that you're going to get much better at as well. You've got to divide by that new power. Think about how you divide fractions. You flip and multiply. So when you divide by 15/14, that's the same thing as multiplying by 14/15. Again, divide by this power. Dividing by a fraction is the same thing as flipping and multiplying by its reciprocal. Let's do it again. Add 1 to the power, you get x to the 16/15. You added a whole, or 15 out of 15. Divide by the new power, 16/15. When you divide by it, becomes times 15/16. And always tack on your arbitrary constant plus c, and that would be your integral.